There's a number in physics that two groups of people have been arguing about for 35 years, and neither group can find its mistake. This is not a disagreement about theory. Nobody is proposing rival models of the universe here. Two sets of experimentalists set out to measure a single quantity, a quantity so basic it appears in the first chapter of every nuclear physics textbook, and they got different answers. The answers have not converged. They have separated. Every improvement in equipment, every reduction in uncertainty, every new generation of graduate students taking over the apparatus has made the disagreement sharper rather than smaller. In September of 2025, roughly 40 people representing every operating experiment in this field met at the Paul Scherrer Institute in Switzerland for the specific purpose of admitting they still cannot explain it. Jeffrey Green of the University of Tennessee, who has been working on this problem since the 1970s, opened the meeting by walking everyone through 5 decades of measurements. 5 decades. Still open. The quantity in dispute is the lifetime of a neutron. And I want to say up front why I find this so much more interesting than most of the big cosmic mysteries. This is not a question about the edge of the observable universe or the inside of a black hole, where we can shrug and say the physics is extreme and our instruments are far away. This is a benchtop measurement done indoors, with equipment you can walk around on the most thoroughly studied particle in nuclear physics. 2 rooms, 1 number, different answers. So let me explain what a neutron lifetime even is, why the number is load-bearing for a surprising amount of physics, how the two methods actually work, and what happened when somebody proposed a genuinely thrilling explanation and then reality took it away from them. A neutron sitting inside an atomic nucleus is stable. The carbon in your body contains neutrons that have not changed in billions of years and will not change for billions more. Pull one out of the nucleus, though, and it starts dying immediately. The reason is a very fine margin in mass. A free neutron is about 0.1% heavier than a proton. Not much, but in particle physics, heavier means unstable if there is a lighter configuration available, and there is. The neutron converts one of its down quarks into an up quark, and in doing so, it turns into a proton, spits out an electron, and releases an antineutrino to balance the books. This is beta decay, and it runs on the weak nuclear force, which is called weak for good reason. It is so feeble that this conversion takes on average about a quarter of an hour. That 0.1% is worth pausing on. If the neutron had come out slightly lighter than the proton instead of slightly heavier, the arrow would point the other way. Protons would decay into neutrons. There would be no stable hydrogen anywhere in the universe. No water, no organic chemistry, no stars burning the way ours does. The entire periodic table sits on the correct side of a margin of about 1 part in 1,000. So the neutron decays. How fast? The honest way to phrase it is that neutrons do not have an expiry date. They have a probability. Any given free neutron might decay in the next second or last an hour. What physicists measure is the average across an enormous population, and the standard quantity is the mean lifetime, which sits somewhere close to 880 seconds. About 14.5 minutes, somewhere close to, that is where the trouble starts. Before I get to the two methods, I need to convince you that this number matters, because a 15-minute particle sounds like a footnote, and it is not. Go back to the first few minutes after the Big Bang. The universe is a dense soup of protons and neutrons, and at the very beginning they are converting back and forth freely, held in roughly equal numbers. Then the universe expands and cools, and those conversions shut off. At that moment, the ratio of protons to neutrons freezes, at roughly 7 protons for every 1 neutron, because the slightly heavier neutrons are slightly harder to make. Here is the part that matters. Those neutrons cannot form helium yet. To build a helium nucleus, you first have to build deuterium, and the universe at that instant is still hot enough that every deuterium nucleus gets blasted apart the moment it forms. So there is a waiting period, several minutes long, before the temperature drops enough for deuterium to survive. And during that entire wait, free neutrons are decaying. It is like a bus that departs only once at a fixed time, and the passengers queuing for it are dying while they wait. The number who make it aboard depends on exactly how fast they die. Every neutron that survives the wait gets locked into a helium nucleus and becomes stable forever. Every neutron that decays first becomes a hydrogen atom instead. That is why roughly 24% of the ordinary matter in the universe is helium, and almost all the rest is hydrogen. That percentage is set directly by the neutron lifetime. We can measure the primordial helium abundance in ancient gas clouds. Astronomers find galaxies with almost no heavy elements, meaning very little star formation has happened there to contaminate the original mixture, and read the helium fraction out of their spectra. Then they extrapolate back to what the composition must have been before any stars existed at all. We can calculate what that number should be. Comparing the two is one of the strongest tests we have that our picture of the first 3 minutes is correct, and the neutron lifetime is an input to the calculation. Get it wrong by 1% and the prediction shifts. It is not only cosmology. The neutron lifetime feeds into the rate at which the sun's core fuses hydrogen. It feeds into models of what happens when a massive star collapses. And it feeds into a very precise internal consistency check on the standard model of particle physics itself. The theory says quarks can transform into one another, and it organizes the probabilities of every possible transformation into a grid of numbers. The theory then makes a hard demand. Take the top row of that grid, square each entry, add them up, and the total must come out to exactly 1. Not approximately 1. Exactly. It is a conservation requirement, and there is no room in the standard model to negotiate it. The largest entry in that row is measured most cleanly from neutron decay. So if the sum comes out to something other than 1, either the measurements are wrong, or there's physics beyond the standard model hiding in the gap. The neutron lifetime is one of the 2 ingredients in that test. So this 15-minute particle is holding up a lot of ceiling. Now, the 2 methods. The first is called the bottle method. The idea is beautifully simple. Take a large number of neutrons, put them in a container, wait a while, and count how many are left. Do that for several different waiting times, and you can fit the decay curve and extract the lifetime. You never need to observe a decay. You only need to count survivors. The problem is that neutrons do not sit still. They are electrically neutral, so you cannot hold them with electric fields, and ordinary neutrons move at kilometers per second, which means they punch straight through the walls of anything you put them in. The solution is a class of particles called ultra-cold neutrons. Slow the neutrons down far enough, to speeds of only a few meters per second, slower than a person jogging, and something strange happens. They start reflecting off certain materials instead of passing through, the way light reflects off a mirror at a shallow angle. Get them cold enough, and you can pour them into a bottle, and they will bounce around inside it. Making them is not trivial. At Los Alamos, the neutrons are produced by firing a proton beam into a tungsten target, then slowed in stages, first through cold graphite, then through solid deuterium held a few degrees above absolute zero. Each stage strips away energy, and what comes out the far end is a trickle of neutrons crawling along at walking pace, and you have to catch them before they decay, because the clock has already started. For decades, that is exactly what people did, and it introduced a systematic error that haunted the field. Every time a neutron hits the wall, there's a small chance it gets absorbed or scattered out rather than bouncing cleanly. Those neutrons vanish from your count, and your apparatus cannot tell the difference between a neutron that decayed and a neutron that got eaten by the wall. Lost neutrons make the population fall faster than it should, which makes the measured lifetime come out too short. Experimentalists knew this and fought it for years. They varied the size of the trap, varied the coating on the walls, extrapolated to the ideal case of 0 collisions. It works, but it is a correction, and corrections are where errors hide. So the current generation of bottle experiments got rid of the walls. The leading one is at Los Alamos National Laboratory in New Mexico, and it is called UCN-Tau. Instead of a material container, the neutrons sit in a bowl-shaped array of powerful permanent magnets. Neutrons have a magnetic moment, which means a strong enough magnetic field pushes them away. The field holds them up from below and from the sides. Gravity holds them down from above. The neutrons float in a magnetic bowl with an open top, and they never touch anything at all. Then you wait, lower a detector in, and count what remains. That experiment gives a mean lifetime of about 877.8 seconds, with an uncertainty of roughly 0.3 of a second. That is a measurement precise to about 1 part in 3,000. Now the second method. The beam method attacks the problem from completely the other side. Instead of counting survivors, count corpses. At the National Institute of Standards and Technology in Gaithersburg, Maryland, a beam of cold neutrons flows continuously down a pipe. Somewhere along that pipe sits a trap that captures the protons produced by any neutron that decays inside a precisely defined volume. Protons are charged, so you can hold them with electric and magnetic fields, funnel them onto a detector, and count them one at a time. Separately, you have to know how many neutrons went through that volume in the first place. That is done with a very thin detector containing lithium, thin enough that it absorbs only a tiny and calculable fraction of the passing beam. Then the arithmetic is straightforward. If you know how many neutrons passed through and how many of them decayed in the process, you know the decay rate, and the decay rate gives you the lifetime. The 2 methods share almost nothing. Different particles counted, different traps, different detectors, different failure modes entirely, which is exactly why physicists have historically trusted the comparison. When 2 techniques with nothing in common land on the same number, you can be fairly confident the number is real. The beam experiments give a mean lifetime of about 888.1 seconds. The difference is about 10 seconds, roughly 1%. And I want to be precise about why 1% is a catastrophe rather than a rounding error. The bottle measurement claims an uncertainty of about 0.3 of a second. The beam measurement claims about 2 seconds. The gap between them is 5 times larger than the larger of the 2 error bars. The combined significance now sits at roughly 5 sigma. 5 sigma is the threshold physics uses to declare a discovery. Except this is not a discovery of anything. It is the confidence with which we can say that two groups of extremely careful people measuring the same property of the same particle cannot both be right. Imagine two bathroom scales, each accurate to within an ounce, one insisting you weigh 200 pounds and the other insisting 202. That is the situation. Not a mystery about the universe, a mystery about a room. Now for the part that makes this genuinely strange. Through the 1990s, nobody was worried. Both methods were imprecise enough that their uncertainties overlapped comfortably. Everyone assumed the numbers would converge as the equipment improved, because that is what normally happens. Better vacuum, better detectors, better statistics, and the two camps walk toward each other and shake hands. They did improve, enormously. Uncertainties on both sides fell by an order of magnitude. The numbers did not move toward each other. What actually happened is the most uncomfortable outcome available. Both central values stayed roughly where they were, while the error bars shrank underneath them. A disagreement that had been invisible inside the noise emerged, sharpened and hardened into a contradiction. In 2005, careful beam measurement at Gaithersburg by Jeff Nico and colleagues put the gap at about 3 sigma. A later recalibration of that same experiment did not shrink the difference. It confirmed it and nudged the significance higher. That is the signature of a real effect, not a statistical accident. Random flukes wash out when you take more data. This one has done the opposite for 3 decades. So people started looking for the systematic error. Hard. Both communities have audited each other's work in detail, visited each other's laboratories, cross-checked each other's analysis. Jeffrey Green, who has spent his career on the beam side, has said plainly that if anyone knew where the problem was, they would have found it by now. And then, in January of 2018, 2 theorists proposed that there is no error at all. Bartosz Fornal and Benjamin Grinstein, at the University of California, San Diego, started from an observation that sounds obvious once you hear it and had somehow gone unexploited for decades. The 2 experiments are not measuring the same thing. The bottle counts disappearances. It tells you how fast neutrons stop being neutrons, and it does not care what they turn into. The beam counts protons. It tells you how fast neutrons turn specifically into protons. Those are the same number if and only if every neutron that decays produces a proton. Suppose it does not. Suppose that about 1% of the time, a neutron decays into something else entirely. Something dark, something that does not interact with ordinary matter, something a proton trap would never see. Run the logic through both experiments. The bottle still counts every disappearance, including the dark ones, so it measures the true total lifetime, 878 seconds. The beam misses the dark decays completely. It sees fewer protons than it expected, concludes that neutrons are decaying more slowly than they really are, and reports a longer lifetime, 888 seconds. The required branching fraction to reproduce the observed gap is around 1%, which is not a strained or exotic number. It is exactly the sort of thing a small coupling to a hidden sector would produce. If that were true, then this decades-old measurement discrepancy is not an embarrassment at all. It is the first direct observation of dark matter, found not in a detector a mile underground or a collider ring in Switzerland, but in a tabletop experiment that has been quietly running in Maryland since the 1990s, while everyone assumed somebody had miscalibrated something. The idea was electric, and the reason it was such good science is that it was immediately, brutally testable. If neutrons can decay into dark particles, then some versions of the model predict a photon of a very specific energy comes out alongside. The team at Los Alamos went and looked for exactly that photon, with the neutrons they already had trapped. They found nothing at anywhere near the required rate. The harder constraint came from an unexpected direction. Neutron stars. A neutron star is, to a decent approximation, an enormous ball of neutrons held up against its own gravity by quantum pressure. If a neutron can convert into a dark particle, then inside a neutron star it will, and the dark particles will accumulate. Because they do not feel the same pressure, they do not push back as hard. The star becomes easier to crush. Physicists call this softening the equation of state, and it puts a ceiling on how heavy a neutron star can get before it collapses into a black hole. Several groups ran that calculation in 2018. With dark decay switched on at the level required to explain the lifetime puzzle, the maximum stable neutron star mass drops to well under 2 times the mass of the Sun. We have observed neutron stars heavier than that. One of the best measured, a pulsar cataloged as PSR J0740 plus 6620, comes in at roughly 2.08 solar masses. It exists. It is not a black hole, which means neutrons in its interior are not dark decaying at the required rate. The hypothesis can be rescued, but only by adding a repulsive force between the dark particles to stiffen things back up, which is the kind of patch you apply when you have already decided the answer and are working backwards. The consensus moved fairly quickly. Dark decay is almost certainly not the explanation. Dark decay was the most elegant idea. But it was not the only one, and the others are still standing mainly because nobody has managed to rule them out yet. One proposal involves mirror matter, a hypothetical duplicate copy of ordinary physics, with neutrons occasionally oscillating into their mirror counterparts and effectively vanishing from the bottle. Another, from a group in Vienna, suggests that neutrons produced by different methods might not be in identical internal states, so that a beam neutron measured shortly after production and a bottle neutron that has been bouncing around for minutes are not quite the same object. A third line of thinking asks whether the sheer number of collisions inside a trap could nudge the decay probability upward, which would predict that smaller traps give shorter lifetimes. None of these is widely believed. All of them are cheaper than admitting nobody can find the mistake, which puts the field back where it started, except now with the added indignity of having had the exciting answer and lost it. There is one more development, and it is the one I think will decide this. For 30 years, there were only two methods. Now there's a third. At the Japan Proton Accelerator Research Complex, a team has built a beam experiment that does not count protons. It counts electrons. Every beta decay produces an electron alongside the proton, and detecting the electron instead means the experiment shares the geometry of the beam approach, while having almost entirely different systematic errors from the Maryland version. They run a pulsed beam through a gas detector and compare the neutron decay events against a reference reaction with helium-3, whose rate is known extremely well. Their first result in 2020 came in around 898 seconds, with uncertainties of 15 or 20 seconds. Far too loose to arbitrate anything. They spent 4 years improving it. Bigger beam transport, better control of systematics, roughly a 5-fold gain in precision. The result they published at the end of 2024 was about 877 seconds, with a statistical uncertainty under 2 seconds and a systematic uncertainty of around 4. That number sits on the bottle side. It is not decisive. The systematic uncertainty is still large enough that the beam value is not excluded, and one measurement does not overturn 30 years of careful work by anybody. But it is the first genuinely independent third opinion this argument has ever had, and it did not land in the middle. Here's the piece that rarely gets mentioned outside the field, and it is the one that shows how thoroughly this problem is being surrounded. The cleanest possible experiment would be to measure both quantities at once in the same apparatus with the same neutrons. Put a proton detector inside the bottle. Then you're counting total disappearances and proton production simultaneously on the same population under the same conditions. If the two rates differ, something is genuinely decaying into something invisible. If they agree, then the discrepancy lives in the comparison between laboratories rather than in the physics, and one camp has a systematic error to go find. That experiment is being built at Los Alamos. Meanwhile, the beam side is not standing still. A substantially upgraded beam experiment at Gaithersburg, aiming for uncertainties several times smaller, is under construction. The magnetic bottle at Los Alamos is being upgraded as well, and a separate experiment at Oak Ridge is nailing down the second ingredient in the standard model consistency test, the number describing the relative strength of the two ways the weak force couples to the neutron, which combines with the lifetime and lets you cross-check the whole picture against completely unrelated measurements from particle decays. Within a few years, one of these will break the tie. Somebody right for 30 years will stay right, and somebody who has been equally careful and equally confident will have to publish the correction. I keep thinking about what this looks like from outside. Some people have spent their entire working lives on this, not on a grand unified theory, not on the origin of the universe, on one number, describing how long a single kind of particle survives when you take it out of an atom. They have built magnetic bowls to hold neutrons without touching them. They have counted protons one at a time. They have gone through each other's calibration data line by line looking for a mistake, and found nothing, and gone back and looked again, and the number they are fighting over is the number that determined how much helium came out of the Big Bang. It is in the light of every star. The hydrogen in the water you drank this morning is hydrogen, because a neutron did not survive long enough to find a partner. 3 minutes into the existence of everything. We know that number to about 1 part in 3,000. We just cannot agree which 1 part in 3,000 it is. Physics does not usually get to have problems this clean. Most open questions are open because the phenomenon is too far away, or too energetic, or too small to reach. This one is open because 2 rooms full of careful people disagree, and both rooms are still standing. The equipment is still running tonight. One of them is wrong. We are going to find out which. Thanks for watching. I will see you in the next one.